degrees or whatever, right? You don't like to have those type of meshes in your geometry, in your solution itself, because it can give you really the erroneous results that at the end of the day you come. It may work, you can get a solution out from the software itself, because the software that you use has a lot of safeguards. They will do something to make it run, but it doesn't mean that the solution is right, okay? It gives you the impression that you got a solution, but at the end of the day, it doesn't mean it's going to be right. So you are, as a CFD user, should know how to decipher your results or check your results at the end of the day, right? So the CFD tool that you have from ANSYS is just a tool. It doesn't have any artificial intelligence to tell you that the solution is wrong, okay? You have to put in the intelligence into the tool to use. So you become, at the end of the day, the CFD expert, not the software. So at the end of the day, I'm teaching you to be the CFD expert, not to be a proficient user of the ANSYS software. I'm not teaching you that, okay? You are becoming the CFD expert. You could be better than me 100 times at the end of the day, okay? And I hope that you would be, okay? But I'm giving you the tools and the experience and the expertise at the end of the day to go out and just to be a CFD expert. And I hope I can achieve that, all right? So the whole purpose of this course at the end of the day is to teach you what are the things you can look for from a computational fluid dynamics aspects, you know, so forth. So what I'm going to demonstrate to you after this slide itself, I'm going to solve a flow in a square dart pipe, okay, with dimensions 0.1 meter times 0.1 times 1 meter. So basically, the area of the dart will be 0.1 meter squared, and the length will be roughly 1 meter, right? I'm going to use Workbench to create this problem itself. I'm going to create a geometry, generate the mesh. I'm going to use CFX, okay, as the initial part of the solution to get, you know, set proper boundary condition and fluid properties, to look at some results. And then I'm going to use Fluent to set the same problem and to demonstrate how easy is it to use both softwares. Okay, it's as straightforward as that. So besides that, I'll go to my Workbench. So I have ANSYS 17. I'm pretty sure in the lab you have ANSYS 19. Yep, it's almost the same. The appearance is almost the same, right? I've not upgraded because I'm still very old and like to use the old versions, okay? And I just don't have time to use for the new version, because every year they produce new version. So the first thing you need to do is to go to Workbench, which is there, which is 17. You'll be Workbench 19.1, is it? 19.2, okay? But they're exactly the same, right? Now, I'm pretty sure you can get student access, remote access as well, right? Using the source. That means that you can actually, if you have internet access, you can basically just access the software itself through your student license. The only restriction of student license is that you're limited to even only 500,000 mesh elements. That is the restriction. But even in the lab itself, you are restricted anyway to 500,000. For researchers like myself and like Cheng, who are PhD students, we have unlimited access. Okay, we can go to 10 million mesh if we want to, all right? But for the problems that we're giving to you with this course itself, you don't need 10 million mesh, okay? You got to know how to create a mesh that gives you a very sensible solution within the 500,000 mark. So you can do that, all right? So it's a bit of an art, putting a cleverness into creating a good mesh for the problems that we showed to you. So what I'll do now is I'll create a Workbench. I'll switch on Workbench. I need a chair. It takes a while to load, so be patient. What? I don't have a license because I don't have internet. Sorry, my mistake. Not connected. Ay, 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 ay. Why is there no internet here? Sorry, let me work out this problem. Yeah, kind of Wi-Fi. Okay, I'm in business. I'll close this again. Right. So if you do access a proper license, this is how you should come out. You should come out with a lot of all the options on your left-hand side, which are analysis system and so forth. So you press OK, right? And basically what I want you to do now is to look under the component systems, okay? So what I'm going to do is I'm going to create a geometry of the square dart at the moment. So what you do then is that you just drag it to the other side, and you have the geometry. Right? Okay, so I will teach you step by step in actually how to either you can create your own geometry using design modeler. So I emphasize design modeler. There is another option. What is that, Ching? Base claim. So I hate that, so I rather use design modeler because it's simpler for me. And also design modeler sort of share the similar features like SolidWorks and everything. So what I'm saying is that I'm teaching you how to generate a very simple geometry using design modeler. But if you want to generate a geometry using SolidWorks, great. You can import it into design modeler very easily as well. So I give you the option. So ANSYS is quite a flexible software because you don't need to adopt a certain way of how ANSYS import the geometry. You can use SolidWorks, you can use CATIA, you can use AutoCAD to import it in your geometry. So it's really up to you. So I'm going to start from the most basic one. So you can see starting design modeler, right? Got to wait, of course. So this is how the layout of a design modeler, okay? The only difference, I think, at the end of the day is the version. So this is version 17. Yours should be 19.2. You should have a similar layout that you click in the labs itself. But it should be the same features. So what I'm going to do now is that I'm going to create now the geometry. I'm going to go through a YZ plan. Why I want to do YZ? Because I like it. All right? So you can use XY plan, ZX plan. It's up to you, okay? I'm not giving you a rules what you have to follow whatever I want to do. I like to use YZ because I just like it, okay? All right? So the first thing you need to do now is you go through to sketching, right? If you scroll down a bit, what I want to do is I'm going to use the rectangular option to generate the squarish area of the 0.1 meter squared area. So I click the rectangular, I go at the 0, point at the corner there, and then start to draw a thing. Now, you notice that also I've drawn a bit too big as well because you can see that the scale is 10 meters. I need to go down this. So I'm going to go back to modeling. I'm going to delete that. As a matter of, you can delete your sketch quite easily, right? You can just delete it. Okay, you say yes, it's fine. So I just want to go down to at least, if you look at the scale there, so that means that if you look at what you want to generate for your area itself, you can basically zoom out to the point to get the scale you want. So I go back to sketching again. I go back to rectangular. I'm going to set the area there. Okay, and you can see then that is a sketch I created for sort of a squarish area. But is it the right dimensions? Of course not. What you need to do then, you got to go back to dimensions to actually indicate, all right, the dimension required. I'm not too bad after all. So you can see for V1 is roughly 0.3 meters and VH2 is 0.21. To put the actual dimensions of the area to be 0.1, all I need to do then is to go back to 0.1 here and I set the 0.1 there. And I got what I want. Okay, this is the exact area of 0.1 meters squared. Okay, very straightforward, right? Okay, now how do I now generate a three-dimensional geometry? It's actually very straightforward as well, right? So what I'm going back to the modeling part. Okay, click the sketch. I'm going to extrude to 1 meter. Now, there is a few options here. In the operations, you can actually designate a material for the domain. But because I don't want to, you can actually change it to add frozen. Add frozen is anything that you want for the geometry. You're not targeted to be a solid material. When you add material, it's more on actually indicating it is a solid material. If it's a fluid domain, just add frozen. Okay? It can be any type of fluid domain that you want to have. Now, if you look at this, the depth itself has been automatically or by default set to 1 meter. You can change that the measure to be 10 meters, 5 meters, it's up to you. But since it's 1 meter, I'm going to accept it, and you just put generate. Bang. That's the geometry that you have. Okay? So that is basically the square art that I'm going to solve. Now, that's very straightforward, right? It's not very hard, right? Now, I'm going to do a few more things here to actually make my life a bit simpler, to see where's the inlet face and where's the outlet face. Now, I'm going to indicate the inlet face to be that face there at the back of the dart itself, and outlet on the other face. Now, to do that, I need to actually twist it around a bit. I'm going to go to Tools, Name Selection, indicate it's a face, indicate that that's a face, and then I'm going to generate it. All right? So if you click on Name Selection 1, I've actually indicated that face to be Name Selection 1, for example. Okay, I'm going to twist it around again. I'm going to do for the other face itself. Again, I go to Tools, Name Selection, indicate that face, and I'm going to generate it, right? So if I click on Name Selection 1, will be that area at the back there. Name Selection will be that area. So I'm going to put Name Selection by renaming it to be Inlet, and the other one to be Outlet. Oh, sorry. I don't want it to be capitals. It doesn't really matter whether it's capital or not capital. So by indicating which is inlet, which is outlet, I've actually generated my geometry already. Okay? So there are other features you can put it in. Now, this geometry is so simple, I can generate using Design Modeler. If for more complex geometry, you can actually read in through SolidWorks or so forth. Okay? And then you can do the same thing of what I've done to actually indicate which is the inlet face and outlet face. Okay? What I'll do is I'll just minimize this. The next thing is to generate the mesh, right? So what I do, you look at the mesh option here, just drag it to the other side, okay? And then you link the geometry to the mesh, right? And now you see that the mesh, now you need to refresh. All you need to do is just to click the mesh to activate it. So it's now you say starting meshing. So what you have done here is that once you create the geometry now, it's being transferred to the meshing component of ANSYS itself. Right? And you can see that it's coming up, and you see the mesh. Right? Now, I'm going to, for argument's sake, I'm going to generate the mesh. I'm going to ask you a question. Okay? Is this a good mesh? Why? Huh? Too large, too coarse, right? Okay, you can see how many elements are there on the face? Only 4. Right? So you can just imagine that you basically have maybe like, if you take the center of the element as where the flow is going to come out, you basically have 4 points, right? So CFD is about meshing. That's why I re-emphasize it's all about meshing. And it's about mesh resolution as well. Now, what I'm going to teach you here is that how you can actually to regenerate the mesh using the divisions of elements that you require. So the one option here is that you click on your right-hand things. You got Insert, Sizing, right? And the thing you have to do now, you can either select a face or an edge. I'm going to select edge, right? Because I want to have the divisions I want on the edge to reflect the mesh on the surface. So I click the first one, press the Control button, and get the rest of that on the inlet and outlet face. So basically what I've clicked, I have clicked 8 edges. So when you go back to here and apply, you have 8 edges. That tells you whether you have indicated all the edges. If you are not, you've got to repeat the whole process again. Okay? Now, you go to element size. Instead of element size, I prefer number of divisions. So let's say I'm going to divide it to maybe 21 for argument's sake. You can do to whatever you want, right? Oh, sorry, not 201, sorry, 21. Now, there is an option here whether you go soft or hard. Hard means that you divide to according to that 21. Soft means that the software will use a bit of its intelligence to say that, no, I'm not going to follow you. I'm going to put what I want, but within the range of 21, 19 or so. I'm going to put hard at the moment, and you can see the result. So I'm going to regenerate the mesh, all right? And I'm going to let you have a look whether I've done it. Okay? Notice, if I zoom in here, zoom in here, you see what the software has done is that it has got the face right, but along the length itself, it sort of put more mesh towards the inlet itself. Okay, so this is how automatically it tries to do. It tries to resolve the mesh where you have the activity coming in, right? So I'm going to minimize this again. I want to divide this along here to also to the specific, along the length of the dart to the specific division I want. So I'm going to repeat the process by actually insert a sizing again, right? Now I'm going to twist this a bit because or else I can't get the edge itself. So what I'll do is, I don't need that, sorry. I will delete again, I'll do it again. Okay, so I'm going to insert sizing again. I'm going to put this, click that, click that, click that, click that, apply for edges, number of divisions, 21, hard, and regenerate the mesh. See, so now you can see that what I've done, I've divided uniformly along the x direction itself. So you can choose your whatever meshing you want. Now, what I've done here is just doing a uniform division, right? If you look at the edge sizing itself, you have the possibility of bias if you look at the bias. So that means that if I click that, you can have basically, look at that, is that the first one is to say that it's moving away from the surface and you have more mesh on the other side, right? And basically, if you look at this itself means that it is more towards the boundary but less in the middle. So that's where how you resolve your boundary layer if you need to. At the moment, I have no bias, so that means that it's totally uniform. So you can play around with the software to redistribute your mesh or concentrate your mesh to whatever you want. Now, I'm happy with the mesh at the moment because I'm getting the resolution that is required, just for a demonstration. Okay? For more complex geometries, you may have to tinker around or may have to use some bias to actually look at your division. At this stage, it looks pretty good, right? So I'm going to minimize then. I'm going to solve the problem. For the problem itself, you can see that there's an option here called CFX or even Fluent itself. Even though you look at itself, you have even the, how do I say, you have the mechanical model here as well, mechanical ABDL. So that means that within the ANSYS software itself, you can even look at the fluid structure interaction. So that means that what happens is that the pressure of the flow can affect the movement of the structure itself. So you can actually have a coupling, fluid structure coupling, within this workbench itself, and it will set up automatically for you. Of course, it's more complex, but you can do that. So for example, if you want to look at how a flagpole is influenced by a wind, for example. So basically, the flagpole will be flapping. So you can do that within the CFX, within the ANSYS domain itself. At the moment, I'm just focusing on the flow, but you can basically create another mechanical model to actually solve that problem. So the mechanical model in this ANSYS is using FEA. Anyone of you doing FEA course this semester? Yeah, you did it. So basically, so what it does is that it creates an interface where it feeds the information from the fluid domain to the FEA model. And the FEA will do the structure deflection and so forth. So you can actually perform a fluid structure interaction using the ANSYS software. Okay? So as I said before in my slide, I'm going to use a CFX option first. I'm going to drag it over again, right? So the CFX domain will come up as it shows. What I need to do then is to connect the mesh to the CFX component itself to the setup, right? So you can see that in the mesh itself, you need to update. So you basically need to update that first. So that what it does is that it now, the mesh information is put into the setup of CFX now. And now, based on that, you can go to the setup. It's going to start the CFX pre, right? So basically, if you look at CFX itself, there's a preprocessor, solver, and a post-processor. So that's where the framework comes in, which I demonstrated to earlier, why you should keep the CFD framework all the time. There's a preprocessor, solver, and a post-processor, which is the results part. Okay, now, so basically what happened here is that from the mesh itself, right, it sort of now puts into the setup of CFX itself. Now, the first thing I need to do from CFX is I need to indicate what type of fluid is being solved. By default, if you go to default domain, right, if you click the default, by default, it solves for air at 25 degrees C, right? You can change the material property either for ideal gas or even water, right? Now, even this itself, you can create other materials itself coming in through some of it here. So you can see you can even insert other material as well, other fluids that you want to solve. Okay, for argument's sake, I'm going to solve for air at 25 degrees. Okay, I'll keep it as it is. Right, yeah, I got to do this. And I say apply, fine, okay. Now, the fluid now is air, okay? That's the working fluid. By default, CFX assumes that all the boundaries of this domain are walls, by default. So you don't need to handle whether it is a wall or not a wall. By default, it is a wall. So that means that if it is a wall, I need to just to define where the flow is coming in and where the flow is going out. Mass conservation, right? Okay, mass in, mass out. So all you need to do is you go to this option here, where you got to insert boundary. Now, you can name the boundary inlet or boundary one, it doesn't really matter. Okay, I'm just going to use a default setting, right? So basically, you remember that why I took a lot of effort in the drawing the geometry to indicate that one of the surface to be inlet, so that when I look at the location, I just go to inlet, okay, which is that face to be the inlet. That's why I say sometimes a bit of a planning, a bit of actually you're doing right at the front when you create a geometry makes life a bit easier when you start setting up your geometry, not to run. For argument's sake at the moment, I'm going to put a speed of 1 meters per second, which I know is going to be turbulent. So if you look at why it's turbulent, you have the turbulent. So by default, CFX assume that the flow is turbulent. Okay, that's by default. Okay, and that's why you have the option of medium density now. I'm not going to describe what I mean by medium or whatever. I'll tell you later as you come to my lectures on turbulence. Okay, just accept the fact that this is a default setting and it's acceptable for the time being. And I say, okay, right? So what I've done is I've set out the inlet face to this domain itself. Now I'm going to set the outlet. Same process, boundary 2. Instead of inlet, I put outlet. So if you look at some of the options here, where you have opening, wall, symmetry, which I'll discuss a bit in week 4, I guess, for the boundary conditions itself. Why, at which cases you can assume symmetry or what is opening and so forth. For the time being, we just know that the flow is going out from the surface and we put it as outlet, okay, for the time being. Outlet, and basically I know the surface is outlet. I go to boundary details. I put the relative pressure of 0. Why 0? Yes, static, okay? So what CFX does of you, it calculates the dynamic pressure, right? So basically, it does from the dynamic pressure, it gives you the results in absolute pressure later, right? But in cases when you solve the equation, it's based off the dynamic pressure. So basically, the reason you set 0 because it's static pressure, okay? The static pressure is 0, okay? And we just say, okay. Right, now, basically what I've done, I'm ready to solve this problem. But I'd like to show you a bit of what the solver control is all about. You know, remember I said that if you look at the solver process, it involves the initializations and monitoring, you know, solution and so forth. By default, CFX initialize your solution to whatever they feel is appropriate for you. Sometimes you don't need to consider that. But sometimes you do need to consider for certain problems where you want to initialize your problem to a certain value. You can do that, okay? Right now, when you start to go to so-called the solution control itself, this becomes where you will learn more throughout the course structure itself. What do you mean by advection scheme, numerics, and so forth? So that is somewhere after week 6, where you look at discretization and so forth, and this makes more sense to you than that. Just for the time being, just accept it as it is, where these are all the default settings. If you can look at, if you drop down the window, you can see it's upwind, high resolution, specific blend pattern, and everything. Okay, you will know this much more throughout you know, the course itself. But there is a purpose for all these features to be there, right? So for argument's sake, we look at high resolution. So high resolution means that it's a high-order numerical approximation method for this problem, okay? And then if you look at this one itself, the turbulence option, they assume to be first order. Now, there is a reason why it's a first order. Because we know that we need to confine the turbulence parameters to be all positive values. Because turbulence parameters cannot be negative. So that means that if you do get a solution, your turbulence parameters is negative, something is wrong. Okay? Right? So that is an indicator for you as well, to see whether your solution is right or solution is wrong. Now, another thing you look at here also is that the maximum number iteration is 100. Now, you can change this. Okay, by default, it's set to be 100. Some solution takes 1,000. Some solution even take 2,000. It really depends, okay? For this problem itself, I know 100 is enough because it's a very simple problem. You get a convergence before that. The reason why I say it's appropriate because it all depends on what criteria you set here, 1e minus 4, right? Fluent, you will see that you're set at 1e minus 3. You'll see it later. Okay, that depends on the software, but this is a normalized value. So that means that the way that the software does is that it is a real value divided by something. That something is I will never know, because they have tested their solution against a range of problems, and they found that 1e minus 4 will give you acceptable convergence. Okay? Now, in your report, your group project, you should change this value to change the sensitivity. That's where is your verification component comes in. You can set it to 1e minus 5, 1e minus 6, to see the sensitivity of your results at the end of the day. Okay? You can explore the scheme, okay, to see how accurate your solutions are, and so forth as well. So this is something you should perform in your group project, okay, to look at the sensitivity of the result. So for argument's sake, I'm going to assume that this is fine. Okay, I say, okay. Now I can start solving the problem. So now I'm going through the solution process. I've set up my boundary conditions. I've set up my working fluid, which is air. I'm going to solve the problem. Okay, another note as well. If I go back to the default domain, you can see that under the fluid models, I'm solving a K epsilon model. And some of you say that, what the hell is K epsilon model, right? So a lot will be revealed later in week 5 when I teach you about turbulence and why it's K epsilon. So let me just say this. By definition, K represents the turbulent kinetic energy. Epsilon represents the dissipation of the turbulent kinetic energy. Now, it's a very handful. But you will know later what I mean by K epsilon, because by the end of this course, you know what is K epsilon. And you can brag about your friends. You know, I know K epsilon. You know, I know K epsilon. And you also see some of the features here is that You have even like shear stress transport or even Reynolds stress models or whatever you want to solve, okay? So there are a lot of models that you can use for turbulence. If you note here, turbulence, when you look at K epsilon, is a model, M-O-D-E-L, model. What it also means is that it doesn't mean that K epsilon can solve everything. All right? It's a model. When you have a model, you need to validate. You got to make sure that the model works for your problem. Or else, you have to explore other models to see their performance against your specific fluid problem. So when you go outside, to do a consultancy project, don't think that K epsilon can solve everything. You have to do a try and error to see which model is the best, right? And I will describe to you some of the features of this model and also to give you a knowledge, a basic knowledge of why certain models are better than other models. Because if you have a targeted problem to resolve certain parts of the flow, you use this model. If not, you can always adopt the standard model, which is nominally K epsilon. Okay? Right. I'm going to now start to solve this problem using solution. So I'm going to start the CFX Solver Manager. This is the window it comes out. Now, it gives you the option whether you want to solve it as double precision. Okay, double precision is based, okay, if you don't click the double precision, that means that your solution is up to the 8 decimals, basically. Okay, that's what single precision means. Double precision allows you to extend to 16 decimals. So it should be more accurate. But hold on there. 16 decimals means that if you have a lot of mesh, if you solve your problem, it will take longer. So you got to weigh that out, right? All right? And also it depends on how many elements you have for your problem. If you have 10 million mesh, your double precision, it will take you much longer. Because why? You're occupying more of the virtual memory, right? And you have basically, you need to store these values while the code is performing all the calculations, right? But some problems need double precision, especially when you start to go to micro scale and nano scale problems. So you got no choice. Some problems you don't need to. So you can get away, with a single precision, with a quick solution. For argument's sake, I'm going to put double precision because it's not going to affect my performance at this point. Okay? I just say I will start running. Okay? Now, if you look at now when it runs at time, you basically have all the values and you basically have all the residuals that you have at the moment. Now these computers are so fast, electrons are so fast, you can do that within this way because it's a very simple problem. That's why I can do this demonstration to you today because the computers are getting so fast, right? Now, if you notice that the solution has ended, okay, I will just say, okay, the solution has ended. Why the solution has ended? Anybody can tell me? Why is it converged? How do you know it's converged? No, okay, I know it stopped, but why did it stop? This is very important, okay? It's very important. Why did it stop? Yes. What was the criteria? I said before. That's right. You look at that. Right? So what the software does is that it will try to detect all the root mean square residuals, whether it's a velocity, and to see that, it's not trying to say that this is the only criteria. That means that any of these drops below 1e minus 4 is going to stop, right? So that's why you see that it stops at 1e minus 4 at roughly 30 iterations, okay? And I will demonstrate to you that Fluent will stop at 1e minus 3 because it is the criteria that's set for that software itself. And that's how it stops. So you can see that the results now can be viewed in post-processing or whatever, okay? So that means that the solution conversion based on the criteria you set in your preprocessor. If you set 1e minus 5, it will end at 1e minus 5. Now, at the moment, you can see that it's well behaved. the residual drops, nicely converging and so forth. You will see some of your problems, you don't get this. You will see that there are sometimes this could be fluctuating and never reach 1e minus 4. All right? And you ask yourself, what's happening? I know, why am I not getting the convergence? So there's a few things, few guidelines I can offer to you. Go back to see your mesh, that's one part. Go back and see your boundary conditions, that's another thing. Secondly, check whether you make any silly mistakes. Okay? Sometimes the obvious one is a silly mistakes that you're done. Then instead of putting 1 meters per second, you put 100 meters per second, right? Of course, it's not going to converge, all right? So sometimes just do a bit of a check, and see what's going on. Right, so now the solution has converged. What I'm going to do now is to see what my results are. I'm going to click this. Starting CFD post. So this is a post-processor part, right? Now, I'm going to view a velocity vectors at the moment at the mid-plane cutting the geometry, okay? So I'm going to insert, put a location, a plane, and I know the location because it's 0.1 meter length. I put somewhere in between. So roughly 0.05, and I say apply. So that's the plane cutting the domain itself. Now, to get rid of the viewing, I just unclick that. I put vectors, yes. Location, plane 1. I'm going to generate it, right? Now, I'm going to move this around so you can see what's going on. All right. Sorry. Sometimes, Now, so what I've done is that you notice that I didn't put a profile at the inlet. When you specify 1 meter per in the boundary condition, by default, it assumes that it is a uniform velocity coming into the domain. Okay, that's by default, 1 meters per second. So you look at actually even your vectors itself, you can see that it's uniform. It's all the same vectors. But it changes as it moves downstream of the dart itself to some profile. But notice that the profile did not change much. It's sort of getting slower near the boundaries. Why is it getting slower near the boundaries? Friction, right? Right? Because the wall is actually slowing it down. But because you got such a high inertia, right, your middle part is still sort of a strong flow going through the domain itself. Now, I look at this result, it's obvious to me. Is it obvious to you? See, from this result, I can describe you the physics, right? That's what I'm just saying is that when you look at your group project, when you look at your results, it must give you a sense of how you can describe the physics. CFD is not about color pictures. At the end of the day, you use a color pictures to describe a physics, right? Okay, if you look at the velocity profile, you start with 1 meter per second. You end up with a maximum velocity of 1.167 meters per second. That's obvious because you must have a balance between your inertia and your diffusion, right? You should get a profile. But if you do an average of the velocity profile at the outlet, you will still get 1 meters per second. True? Correct, right? So that means that if you slow down at the walls, down to roughly, if it's yellow color, roughly 0.8 meters per second, you must have a high velocity in the middle to balance it out, right? Right? So that means that this is how you check your solution to see whether it's correct or wrong. Now, I'm going to go back, and I know that this is turbulent at the moment. I'm going to solve a laminar flow now to show you the difference between what you got now, the velocity profile, and, okay, the laminar profile. Very straightforward. I'll go back to the pre. Okay? All I need to do is I go back, I say, okay. I'll go back to default domain. I set that to be laminar now. And it comes out to say that there's something wrong with my turbulence because I'm changing it to be turbulent. Because I change it to be laminar, I have to change my boundary conditions. I'm going to set this now to be 0.05. If you calculate the Reynolds number, it should be roughly laminar. Okay, that's how you know whether the flow is laminar or turbulent. So by definition, Reynolds number, you know, if you know, those people know fluid dynamics, is the density times the reference velocity times the reference length divided by the viscosity, dynamic viscosity. If it's anything less than 2,000, you know, also it's going to be laminar for this type of geometry, for more of a conduit. All right. Now I've set the boundary condition. All I need to do is I got to get rid of this. I go back to this. Go back to the workbench. I'll start the solution again. Now this time I want to start from rest. So all I need to do, I go to initial values instead of the previous run, which you can, you know, if you have stopped somewhere, you want to continue running, all you need to do is you can set it the default as it is, or initial conditions, right? Because I saw initial condition, that means I'm going back to the original setting of the problem. And then I start running. You can see that if I start running, I start really from the beginning again. Again, the residual goes down to 1e minus 4. Once it hits below 1e minus 4, it's fine, right? I'll go back to the post-processing. Okay, sometimes it happens, sorry. So I need to go back to workbench. I'll close this. I'll go back to results. I'll repeat, okay? So what is the difference between the previous one and this one? Look at the profile at the outlet. What's the difference? More parabolic, right? Right. Now, why is it so? Okay? As I said before that, you start with a uniform velocity. Because your inertial effect is not as great as your viscous effect, your viscous effect becomes more dominant. So it's diffusing the flow, right? So what it tries to do is that it tries to diffuse us to the point it becomes a parabolic. This is a characteristic behavior of a laminar flow in a duct, right? If you have turbulent flow, because the flow itself, the air takes shorter time to get from the inlet and outlet, you get a flatter profile, okay? Right? So you can see that from the results I showed to you, you can actually describe a lot of things from the results, okay? What are the physical characteristics? What are the things you should observe for? And you can brag to your boss to say, I know all this beautiful stuff, right? Not in addition to color pictures. The color pictures is an attraction, it's a perception. But if you describe the physics, your boss will love you. You know, your boss said, wow, this is fascinating, this is unbelievable. Another thing I didn't show to you that you can even plot out contours. Let's, for example, I try to plot out the pressure to you, okay? So I'm going to put a pressure for the plane one itself, I'm going to apply that, right? And then what I try to do then, I'll click. Now, I'm going to sort of do a quiz for you now. All right? Now, the pressure is highest here, lowest there, right? So it's a pressure gradient. So the pressure gradient goes into the source of the momentum equation, and then basically you have that flow that you describe. But I'm getting a negative 0. Why is that so? Isn't that should be 0? I said 0, but why is it giving negative? Tell me the reason. Huh?
Is it at the outlet?
At the outlet. It is. Blue color. Why is it negative? Huh? But I should be 0. Because I set my boundary condition to be 0. But why is it negative? Why is it a negative value? Is it wrong? Is it right? Or is it partially right? Tell me. You are CFD experts now. You tell me. Nah, it's numerical errors. Okay? So, all I'm just saying is that if you, okay, it depends also, it's a few things, all right? Sometimes you may need to use double precision as one way to overcome your solution. So if you've got 16 digits of a value, you should get more accurate results. Second thing, it could be your discretization, okay, basically your numerical approximation of your terms. Third thing is could be your residual, right? You maybe have terminated your solution too early to get the accurate solution you want. But whatever it is, you will always have numerical errors creeping into your solution. And you got to be aware with that, okay? Negative 1.4057, I can take it. It's a small value. It is close to 0. I'm just pulling your leg, okay? But if it is a negative 0.5, I would say you better check your solution because it's supposed to be 0. Yes? Yeah. Yes. So another thing also is not also that you see that there's a funny line here, right? It's because you specify uniform velocity. So the flow is still developing. So that's why you get a funny line there. By right, it should be straight, right? So if you actually do specify a profile here, which correspond to a parabolic profile, you will not see that line there. It will be totally straight, okay? So this explains that because the flow is still trying to come from a uniform to a parabolic, that's why you got a funny pressure there or whatever. But again, this picture tells you a lot of things, right? It explains to you the physics, So by right, you should be getting basically straight as what you would expect, That's what you should expect. But then you look at the result, you start thinking, I never knew that. Developing. The flow is still not fully developed when it comes from the inlet to the outlet. By right, the flow, if you put this domain to be long enough, will be fully developed at the outlet. And that's what you should expect. Okay? Right? So a negative 1.4 E minus 7 is tolerable. I'm not saying this is a wrong solution. It's just that there are some numerical errors do creep up during your calculations. Right? But this is still an acceptable solution. Okay, so any questions so far? All right, okay, now, I'm going to teach you how to use fluid. It is as straightforward as easy as saying. What I'll try to do, I'll just drag another fluid there. Instead of me setting up the geometry or mesh or whatever, the good thing about Workbench is that you can basically use the existing geometry and mesh to connect directly to the setup. All I need to do is just drag up the mesh and go to the setup. That's all you need to do, okay? And then to transfer the information from the domain, the mesh and the domain right to that, you need to update the meshing. And it's reflected. Note that it's also reflected in CFX as well. So what it does is that Workbench, allows you to set different CFX. You can do a lot of comparisons of software and so forth. Now, I'm going to go to the setup of Fluent. Now, Fluent asks you right from beginning whether you want to solve it as double precision or not double precision. They sort of at the front. Okay, I'm going to say yes. And it gives you the option of solving in a parallel or non-parallel. So parallel means that if you have a 4-core of your computer, you can use all 4 cores. For argument's sake, I'm going to use parallel. I'm going to use 4 cores. Okay? And this is a layout of Fluent. I think this is what appears also in 19, right? Yeah. Okay, I'm going to drag this a bit. Still working. Sorry. Okay, I'm going to drag this a bit here so you see what's going on. Note that it seems that there is a warning here from Fluent. Do you know why? CFX, we didn't have the warning. Why is Fluent there's a warning? Oh, all of you are so stunned. The reason being is because CFX automatically designate any geometry to be a fluid domain. By default, Fluent designate any geometry to be solid. So what you need to do is that you got to go back to the cell, then so got to press the solid and change that to be fluid. Okay? And you say, okay, that solves the problem. Okay? Once you've done that, you solve the problem. But the good thing about Fluent is that when it goes to the boundary condition itself, they already set up whether it's an inlet and outlet for you already, based on whatever you set as an inlet outlet at the point you create your geometry. Right? So if you go to the inlet velocity inlet, I'm going to do exactly the same. I'm going to set to be 1 meters per second. Okay? And by default, Fluent assumes turbulent flow as well as CFX. And also Fluent adopts the same format as CFX by assuming that all the walls are solid unless you specify as an inlet or outlet. So it's the same thing. So that's what I'm just saying is that it doesn't really matter whether you use CFX or Fluent itself. Basically, if you know how to use CFX, you know how to use Fluent. It's not that hard. And I can tell you at the end of the day, even for Star CCM Plus, it adopts the same format. So you can go from one code to another or transit from one software to another quite easily. Okay, I do have Star CCM Plus here as well, but I don't think I'm going to confuse you, okay, because it's going to be a bit more confusion. So what I've done is I set the boundary condition, I'll set the outlet, you can see automatically set as pressure, and it does set at 0 pressure automatically for you. Okay? Gauge pressure to be 0. You say, okay. Now, you notice that if you look at CFX itself, the solver control is less complicated. You have advection to be high resolution and to numeric step. Now, there is a difference, fundamental difference between CFX and Fluent. Now, I'm getting very technical now. In terms of the solver for CFX, it uses so-called a direct solver. What it means by direct solver means that the velocities and the pressure are solved simultaneously. Okay? Fluent, which was developed much earlier than CFX itself, solves the problem sequentially, segregated. So that means that they solve the U velocity first, solve the V, solve the W. This information of velocity goes to the pressure correction, okay, and then it goes back. So basically, this is called the segregated approach. Because you have the segregated approach, you need to make sure that the solution is well behaved by introducing under relaxation factors. Now I'm confusing you. And that is reflected in, okay, the solution controls, right? So these are the default under relaxation factors. You can see pressure is 0.3, and then basically momentum is 0.7. Now, whether you see whether this is right or wrong, it all derives because of the solution method that you are using. So what does simple means? Anyone knows? Simple is not simple, okay? It is more complicated than you think, all right? Okay, so let me give you the answer. Simple means semi-implicit method pressure linkage equation. All right? All right? So what it means by that? Okay. The reason why simple is developed is because when one wants to solve a so-called incompressible flow, you have no means of linking the mass conservation to the momentum. So you got to devise a method to link those two together. So this simple aims to link, okay, the pressure effect of the algorithm or the solution to the mass conservation. So what you do there is that by strongly linking these two together, you satisfy the conservation laws of mass and momentum. Okay, that's what simple means. If you drop down the window itself, you have simplex or simple C, we call it piezo, and then couple. Now, the feature of Fluent that is sort of exactly like CFX is couple. So couple is a direct solver. Okay, all right, but hold on there. Couple for Fluent is not as advanced as CFX. Okay, CFX spent years in developing a perfect solver for their software. So the couple solver in CFX is much better than Fluent. Sometimes it is better to go with the standard. Why? Because sometimes in terms of the normal algorithm of simple, okay, simple C, the C means consistent. Okay, I'm not going to get down to what's the difference, but it means simple, consistent. Piezo means is pressure implicit something already. Pressure implicit semi, I don't know, I forgot. You know, if I give you a history, basically, it involves the calculation of 2 pressure corrections. That means that simple use 1 pressure correction to calculate the solution. Once you get the solution, it goes to another pressure correction to update the mass conservation. So it should be more effective in a sense that you should get faster convergence towards your mass conservation at the end of the day. So, but that's what piezo means, okay? So piezo was developed by a professor from Imperial College, right? So he is the one who developed that, which proves to be quite effective. That's why piezo is there, right? Now, I'm not going to go into gradients and everything, because this is based on discretization, based on triangular meshes and everything. I won't go into that, so you can ask me later. But if you look at pressure and momentum, you have second order or second order upwind. This is what you so-called the advection schemes that you see in CFX, right? Okay, so Fluent goes down to more specific description. So if you look at the momentum itself, you got first order upwind, second order upwind, power law, quick, you know, and third order muscle. We call it muscle, all right? So I wouldn't get down into those things. If you really want to know, I can spend an hour with you to describe to you what discretization scheme is all about, okay? So let's accept that the code is good to go, right? And then you start to look at monitor itself. You look at residuals. Now, you can see that the residual is set at 0.001, 1e minus 3. Again, it doesn't mean that Fluent is not accurate. It's just the way they normalize the residuals. Damn, bugger, system off again. Sorry, the air conditioner went off. It's running again. So what does Fluent does is that it normalizes their residual according to their own way, their own method, okay? So just accept it that they have done a good job and the residual is what it is. But still, if you are using Fluent for your group project, make sure you try other criteria, like instead of 1e minus 3, it will be 1e minus 4 or 1e minus 5 and so forth, okay? Now, solution initialization. If you remember that in CFX itself, we didn't need to bother about this option. It does it for us. Fluent, unfortunately, needs you to do this step, okay? So you need to either you do a standard initialization or hybrid initialization. By default, it's just hybrid. All you need to do is just to press the initialize button. And it will does it for you, you know, hybrid initialization is done. So you need to do this step for Fluent, unfortunately, right, before you can proceed to calculate your solution. Then when you go down to the activities run calculation itself, this is where you set your number of iterations that you want to solve. Let's, for argument's sake, I'm going to put 100. Okay? Okay, now, if you notice that I've assumed that I'm going to get a steady state solution, by default, both codes, CFX and Fluent, set it as steady state. So steady state means that they will speed up the calculation to use a state where you don't have the flow changes with time. That's what steady state means, right? It's running. So if you want to solve to be transient, there are sometimes CFD problems you need to solve it so-called like a time-dependent problem. So you need to set a time step. right? Sometimes that is important because you don't know whether the flow is going to reach a steady state or not. You don't know. And sometimes it's good to march the solution towards a point where it sort of reaches a steady condition. That means that it could be a fluctuating flow, but it doesn't mean it's going to be a straight line. So sometimes you may need to solve the problem using transient to see whether it does exhibit the periodic manner, right? And that says that whether the solution is actually steady or not steady. So I'm going to calculate the solution now. Calculate. Right. So you look at the solution, it ends in 34 solution. By right, it should be reaching 1 e minus 3 somewhere, right? And that's why it terminated, okay? Now, in Fluent itself, you can either view your results based on the post-processing here, or I can teach you that you can even do the results like what you see in CFX. So let's, for argument's sake, I'm using post-processing here. I'm going to plot out the vectors, and I say that it's an interior solid, and I'm going to display it, right? And basically, I'll turn this around. So what I've done is that I'm going to zoom this a bit. Sorry. How do I zoom this? Okay. Right. So you can see that the profile there is roughly flat because of the turbulence again, right? What I plotted out all the vectors of the interior solid. That means at every point within the domain itself, right? So that means that what I've done with CFX, I just plotted a plane, okay? So you can do so many things with the result. Note also that the velocity is slightly different again, because in CFS we got 1.167, right? And here's 1.22. But they're almost at a similar order. But why is it different? Can anybody tell me why is it different? Everybody looks me. The answer is basically coming down to the solution method you use. Okay, as I told you before, that depending on what numerical scheme you use, you will get a solution, okay, for your problem. So but regardless of whichever scheme you use, and also your convergence criteria, you can still see that the solution is still very close. You're not getting like 1.16 and 3.5, for example. Okay, you're not getting that. You're still getting within a certain decimal to be quite close to each other. Now, let me teach you another thing. Right now, you want to view these results, let's say in the previous CFX post-processing. You have the option here looking at here results, drag it there, and you can actually feed your solution into results. Okay, and you can click that. Why you got no license? Oh, but it should be okay. So again, I can use the plane. 0.05, apply, vectors. Okay. Okay. So it's 1.218 compared to 1.167. Okay. So you can so post-processing results itself, you can use anything you want. You can use the Fluent option. You can use the post option by CFD. I tend to like the CFD post a bit better, because the results are more richer, the graphics itself more richer, and you can do that very easily. Okay, I'm going to end this lecture early. You got any questions? Or what else do you want me to show you? I'm open for suggestions. Or do you want to have an early lunch? It looks like it's going to be an early lunch. Oh, before you go, I got a request from Chang, our head demonstrator. Please check your Moodle for your group allocation. It's very important you do that, because today itself, when you go to your tutorials, you should know which group you are in and which problem you are solving, right? Next week. That's next week. Okay, but at least to know your group members of your group, and if you have any issues, talk to Chang, okay, and we can sort it out for you. Hey, good?
Good, I'm really good. I must say, I don't regret not taking CFD as my thesis. But yeah, I'm taking CFD and FBA together, so a lot of concepts.
It should be quite straightforward.
Yeah, I think so. I hope so. I really hope so.
It should be straightforward.
Yeah.
By today, you know everything was here.
Well, later I'll have a tutorial, so let's see.
Yeah, it should be fun.
Yeah.
Yeah.
Thank you for the lecture.
Thank you. Thanks. Yes. Yes. Yeah, I know. Because I can explain whatever I want to explain, right? Like I know, like this is because of this, this is because of that. Yes, I know what you're saying. There are always ways to know what you're comparing against, and usually there is a guideline. Yes. So basically, when you do your group project, you always have a standard, which is experimental data, whatever you do. And basically, if you follow the guidelines, you should be able to get there, because we know the solution. So hopefully, by doing this various steps, you'll get there. But if you don't get it, we'll still help you as well to understand why you're not getting there. Then you go back and say, that is because of this, that, this, that. You can change your language, but it's based on physics again. It's what the velocity you put in. 1 meter is more than 2,000. Yeah, I know it's turbulent. That's why I put 1. I can put 10, and I know it. Yes. They are not entirely different, but they do. There are 2 CFD programs that NC's acquired. The reason CFX is because it started with 4-3D. They changed it to CFX. Let me say this, what is different. CFX does very well with multi-phase flow, like gas liquid flows and everything. Okay? Fluent, yes, right. Fluent does better with particle flow. You know, like solid particles with flow, because they went different directions in developing the approach. So, for example, tracking of particles, I like CFX Fluent more. For like solving gas liquid flows, CFX went with the because I know the developers, so they went to the it boils down to the same thing. In terms of the basic engine, it's the same. But it depends on the models. It's basically boundary condition. How they treat the boundary condition, because they use different ways to treat it. But in terms of the numerical solution, it's almost the same. You know, they should be the same. If you're not the same, you get very worried. Yeah, exactly. You get very worried. So, yeah.
How's it going? Sorry.
Yeah.
I just have a couple of things.
Yeah.
Do you reckon, I know in the first lecture you said, you know, you've got to put in the work for this course. You know, I'm working like 3 or 4 days a week.
Shouldn't be.
Shouldn't be. Do you reckon the bookshop would, for your book, do you reckon they price match the book if I found it online for $10 cheaper?
I hope so. I hope so.
Because I think it's $100 for, it's like 115 in the bookshop and $100 online.
Just buy online then.
But I want to get it today, so I can start studying for it.
Damn it. That I have no control.
No, fair enough.
No, but still, ask the bookshop. Yeah.
And for the major project,
yes. You're talking about the group project or the individual? Individual / group,
or any of them.
Yeah.
Do we pick? We can pick our own things, right? Or
can we pick?
But more importantly, based on the previous experience, most of the students ending up have to give up the problem at the end.
Yeah, most of them actually got it. Just say that. No time. I'm gonna.
That's my case. I end up really bad for this course.
The reason why problem is that because when you choose your own project, you need to find the data to validate.
Yeah, that's the thing. Because
do we have data to validate?
I can. The thing that I was going to do at work. We're installing a new seawater pipe.
Yeah.
And you know, I want to model the flow in it, and I just want to see if I can get similar results to him using my own thing. If I
so put it this way, I think what Chen comes is good, right? But if you can present to us a very validated data, not something difficult, something simple, you know, 2D or whatever, you know, and what you're very passionate about, we can provide concessions. Okay. So don't be because we want to make sure that at least you talk this process through.
Yeah.
This is what I want to do. If you're passionate about it, you're not stopping. Okay. You know, I'm not stopping you. I think it's good.
Yeah.
You know, for some people to come on, you know. But what we have found is that people, they say they have a project. When it's not their project, then they say, I don't know that. I got to go back, you know. But we want to make sure that those who want to go to a project, you know what you're getting is something good.
Because we paid like $50,000 for a CFD guy. It's Dr. Nahab or something. You know, Dr. Nahab, he did I can get the model of him, and then I can ask him for it at the end. And if I get the same results as
well. Go for it.
You reckon?
I got no problems with that.
Yeah.
So think through it. But put it this way, I'm not stopping you from doing your project. It's just based on experience. That's what we do. But I can, you know, I'm quite flexible. We are quite flexible. We're not to say that. That's it. You know?
Yeah, definitely help you. Alright. Yeah. We're in the shoot. Yeah. I'll show you the report.
So for those of you who really want to do your very passionate, you know, I'm not stopping you. You know, because at the end you will get benefit out of it. You know, because you like to solve the problem, you like to solve the problem. Fine. Alright. Go for it. Okay.
Sounds good.
Yeah, I'm not stopping you.
Thank you.
For the individuals, it's looking like I'm going to be away. I'm going to America for 2 weeks.
So I am also quite flexible. I would allow you to say, but that's between you. You just like you have to do just be I'm not going to you know, just tell me before. Okay? Alright, just tell me before, okay?
So this is just supposed to be going on to the geometry, just the raw square.
You're talking about fluid or CFX?
Assume the same boundary.
It's making a difference, so I don't.
Okay, CFX tends to assume that you're always solving a fluid problem. So you are treating it as walls, your geometry to be walls, and everything is hollow inside.
It's assumed.
Yeah, it's assumed hollow. You know? For CFX, you assume that it's not hollow, it's a solid. So yeah,
For fluid.
yeah, for fluid.
You
So you have to change
it
it to be hollow.
Yeah.
Yeah. So fluid always tends to assume that no, I'm not going to take out, I'm going to take it solid. So there's basically a vacuum you can put in.
So when I add the material later on, it's going to assume only the wall as the material,
Yes, right.
and the thing in between is the thing that I just set it like air or water.
That's right.
Okay.
Yeah. So fluid is a bit
Yeah.
tricky here and there. You know, you just gotta tweak a bit, or else you keep clicking the thing. What's the problem?
Yeah, that's okay.
Yeah.
That's okay.
I think.
I have a problem.
Why is that a problem?
I'm doing this for my thesis, so we're like monitoring the hard state. We're trying to optimize the design for it. So I've got this like inlet runoff to make sure the flow is laminar by the time it's extended. I've been doing the meshing for it, and I was asking mesh conversion.
Yeah, that's not good.
Yeah, no, it's not.
You should do this type of mesh where you have a what you. If I can try it, you got a paper? I can.
You can write it down on my surface if you want.
No, I got a paper.
Read the bookshop. I work for some time.
For any cylinder geometry.
10% off one of the recommended retail prices. So you can just go.
Are you doing a research thesis?
Research, yeah, I started last year.
Okay, so for this type of geometry, I always recommend one thing. If it is circular, it's better to create sort of an inner square domain,
Okay.
get something like that, and then you split it, then you get something you join this way, and then basically this will envelope this,
So if I just put like a primitive rectangular through, okay.
just like another domain. You extrude it. So basically then you can control your meshing near the wall.
Yeah, okay.
Because if you triangular mesh, you can't control it.
Yeah, so with like the literature, I'm working with Susan Bayer.
Yeah.
And in all of the stuff they're using, like the method they're using is the tetrahedral.
Nah.
You don't want not a good idea.
You're not going to get the accuracy you want.
Okay.
Because for your problem, you want to resolve what is near the wall.
Yeah.
And you want to get the pressure, for example.
Oh, wall shear stress.
That's
yeah.
right.
Yeah.
I know the problem.
Yeah,
Because I
okay.
do a lot of bioflows.
Yeah.
Okay.
Okay.
So you want to
So
get,
you're doing
so basically by doing this, you can put triangular here. That's not a problem. In
Yeah.
the middle, triangle is fine.
Okay.
It's just because of the resolution,
edges,
around
yeah.
edges, which you need to move to concentrate the mesh where you want to resolve the flow gradients, basically.
Okay.
If you can better resolve your flow gradients, then you get a better prediction of the pressure, and the pressure will give you the water stress.
Okay. The other thing I was thinking about was splitting it up. So before it was just one long tube
Yep.
with a stent. So I've tried to put these sections in because I'm interested in what's happening just past the end of the stent.
Yes.
Like there's recirculation
Yeah.
zones.
What is the geometry of the stem? Is it a circular? Or?
Yeah. So do you mean like the stent struts?
Yeah.
So both. So we're looking at circular and square.
Circular and square.
Yeah. So we've got like 7 different variables we're changing. And then we just got 30 designs generated. We've got to
Do you
analyze
actually
them.
put the circular geometry inside? Or what?
Yeah, so like these struts, I think this is a square one. It's really hard to zoom. I think that's like, I think this, or maybe this is the circular one because it hasn't got the dip in it. So this, I think this is the circular geometry one. So I imported the stent and then
no,
did
the
a
circular
cylinder.
is around it, right?
Oh yeah, it's
Yeah,
round. It's
yeah,
only
yeah,
round.
yeah.
Yeah.
The
But like
meshing-
the struts itself.
The meshing is horrendous.
Yeah. I've ran it by Susan. She's been busy, so I haven't had a chance to
Yeah.
actually see her.
Because I understand where you're coming from. Why you use triangular. But I find that you can have a triangular on the surface, but away from the surface, you still need to have some structure.
Yeah.
Yeah, or else you're going to have problems.
Yeah, because when I read through it, the
Yeah.
tetrahedral patch